This program is brought to you by Stanford University. Please visit us at stanford.edu.
Let's come back to general relativity. Are there any questions?
Yes. You asked to raise the question about the contraction of...
Yes. Good. I meant to do that. Right. You're talking about G mu nu.
Yes.
G mu nu, and G mu nu.
Yes.
Right. Okay. So G mu nu is a tensor with two covariant indices, two downstairs indices. It has a version with upstairs indices, and by convention, or by definition, the G mu nu with upstairs indices, think of this as a matrix. Think of it as a matrix. In the case of four-dimensional space-time, it's a 4 by 4 matrix. I'm not going to write down all of its entries. This matrix is G mu nu, and G mu nu with upper indices is also a matrix. It's also a matrix. It's the matrix of entries with upper indices. But the matrix with upper indices is simply defined as the inverse of the matrix with lower indices. That means if you multiply them together as matrices, what's the result of multiplying a matrix by the inverse of itself? The unit matrix. The unit matrix is the matrix 1, 1, 1, 1, with zeros everywhere else. Won't bother writing the zeros in. All right, that's statement number one. So we have these two matrices, which are related by the fact that their product is the unit matrix. Let's just talk about multiplying matrices for a minute. If I write matrices, a matrix in the form of, let's not worry for the moment about upper and lower indices. Upper and lower indices are very important when you're doing differential geometry and so forth, but just matrices. Matrix with entries A, B. And I want to multiply it by another matrix with whose entries are, or whose indices are, another name, another word, another letter for a matrix. Q? Q, okay. Q. We're multiplying the matrix M by the matrix Q. All right, so the way that you multiply it is just you put MAB next to QBC, and then you multiply the entries and sum over the repeated index. That gives you the matrix product MQAC. All right, so what does that mean about G mu nu and G mu nu here? If we multiply this matrix by this matrix, we should get the unit matrix. All right, so let's use the rule for matrix multiplication. First, we write down the matrix G. Now let's give it, I don't want to use mu nu. I'm going to use some arbitrary indices, alpha and beta. And next to it, this is the matrix with lower indices. Next to it, we put the other matrix that we're multiplying by it, right next to it, G, B, or beta gamma. That's the same combination or the same logic that we have here, MAB, QBC, G alpha beta, G beta gamma, and sum over beta. That gives us a matrix with an alpha entry or an alpha index and a gamma index. Now notice over here we didn't pay any attention to covariant and contravariant components. We just thought about ordinary matrix products. Here we have a matrix with covariant indices, or a tensor with covariant indices, multiplying a tensor with contravariant indices and summing over beta. But that's the matrix product of these two matrices. What is the matrix product? The matrix product is the matrix with ones along the diagonal. That's the Kronecker delta. All right? Now it's from the notation and consistency of notation, I could write that this is delta alpha gamma. Yeah. We don't really want to put that gamma upstairs, downstairs. Why not? Well, just the consistency of tensor notation, covariant and contravariant, sort of suggests or pretty much insists that we put the gamma upstairs. But it is just the Kronecker delta. 0 if alpha does not equal gamma, 1 if alpha equals gamma. So in tensor notation, the Kronecker delta is always a thing with an upstairs index and a downstairs index. So from now on, whenever I use the Kronecker delta, don't be surprised to see it with one upstairs and one downstairs index. That's number one. Now, number two, let's talk about raising and lowering a tensor index. Supposing I have a tensor with upstairs indices, and I want to lower one of the indices. So let's take some general tensor, T beta gamma, and I want to lower the beta index. What I do is I multiply it by G alpha beta and sum over beta. That lowers the index, and it gives me the tensor T alpha gamma. Okay, let's compare that with what's going on here. Here I have the matrix G with upper indices. So we can, it's the replacement, if you like, for T beta gamma in this formula. Next to it, I have the metric, G alpha beta, which is exactly what I have over here. When I combine these two together, what does it give me according to this formula? According to this formula, it gives me T with one lower and one upper index, but T is just G. So it gives me the metric tensor with one lower index and one upper index. So the metric tensor with one lower index and one upper index is always just delta alpha gamma. It doesn't depend on position. It's just delta alpha gamma. It's one of the few tensors that will meet in geometry which doesn't depend on, or one of the few sets of components, which is just a numerical set of components which does not depend on position. G over here may depend on position. G over here may depend on position. But because what's over here is always the inverse of this, delta alpha gamma does not depend on position. It's always just this matrix. So that's the answer to the question, what is the tensor, the metric tensor with one lower index and one upper index? And the answer is that it's the Kronecker delta.
Where did that last G come from?
Say it again?
The last G.
Here?
Where did it come from?
No. From this combination. What is this combination? All right. In this combination here, this G is playing the role of this T, right? Okay. So let's call it T. Well, I don't want to call it T. I'm going to call it G. Okay? But all I'm doing is substituting wherever I see G here, wherever I see T over here, I'm substituting G over here. Okay? The rule is that if you take T with two upper index and multiply it by G, you get T with one upper index and one lower index. Well, what is T? T is G in this formula.
Then is the whole left-hand side equals to G alpha beta?
Alpha gamma.
Yes.
Yeah, equals, yeah. Oh, well, I'm sorry. Okay, yeah, this whole left-hand side is equal to this. By definition. That's essentially a definition. Two definitions going on. One is the definition of how you raise and lower indices, and the other is the definition of G with upper indices, that it's the inverse of the G with lower indices. Right, so whenever you find yourself wanting to use G with one index upper and one index lower, it's the Kronecker delta. Now, that tells you something else. Supposing you want to contract an upper index and a lower index. Supposing you have some tensor, T alpha beta, and you want to form a scalar out of it. To form a scalar out of it, you can multiply it by the metric. Well, first of all, you can just identify beta with alpha and contract beta with alpha, or you can just think of it as multiplying it by G beta, delta beta alpha, which is just G in some other notation. Let's write several different formulas. All right. First of all, there's T alpha beta, which if I want to make a scalar out of it, I multiply it by G alpha beta and sum over alpha and beta. That makes a scalar. All right, that's one way to make a scalar. Another way, which is equal, and you can prove this, I will leave it to you to prove, is to take T with lower components and multiply it by G with raised components. Same thing. That you need to work out, okay, to see that that's true. But you can also take it to be T with one upper index, one lower index, multiplied by G with one lower index and one upper index. They're all three equal to each other. And in this form, this is just the Kronecker delta times T alpha beta. Now, the Kronecker delta is either 0 or 1, depending on whether alpha equals beta. So it's really just an instruction to add T11 plus T22 plus T33 plus T44. And so it's exactly the same as T alpha alpha. T11 plus T22 plus T33 and so forth. I just do this because there was a hole that I left out of the discussion, what the metric tensor is with one upper and one lower index.
If you want to lower an index on a tensor that already has some lower indices, how do you know where the new index goes in the lower?
Well, you have to keep track, in general. You should think, whenever you write a tensor, think of ordering the indices, alpha, beta, gamma, delta, sigma. Now, unless the tensor happens to have certain symmetries, it may have symmetries which tell you that it doesn't change if you interchange the indices, but let's suppose it doesn't. Then you have to keep track of the order of these indices, and if you decide to raise the beta index, put it over here. Okay? Right. So, right. What I said is, if it's a symmetric tensor, then it doesn't matter. Just put it directly above, yeah. In other words, right, it may not look it directly above. In other words, think mentally of putting some partitions in, and you can slide the indices up and down with the metric tensor.
Question?
Yeah.
I think of the metric tensor as sort of given to you, it's there. And
Well,
T is any old tensor that comes along.
Right.
So what is the meaning of that last sentence you have on the board there? In other words, what are you doing to the any old tensor when you hit it with the metric tensor? Besides lowering these things. Is there any sort of physical? Like for example, the term.
Well, that brings us back to the original question of what's the relation between the contravariant and covariant components of vectors. And as I told you, they are connected with expanding the vector in terms of basis vectors or projecting the vector onto basis vectors. The same is true of tensors, but if you like, it's just a way of forming tensors out of tensors, forming tensors with upper indices out of tensors with lower indices. And you give them the same name if they're related by this operation. They have the same information in them. Geometry is the connection between expanding things in basis vectors and projecting onto basis vectors. So I'm really going to leave that for you to go and look up and find some good discussion of covariant and contravariant indices and their geometric meaning. There's lots of places to look it up. Yeah.
Obviously, G has to be invertible. Is there any other
G has to be invertible.
what could be a metric tensor?
Yes. Right. All right. If, yeah. In ordinary geometry, which means geometry of spatial surfaces and so forth, where time is not different than space and you don't have not Minkowski geometry, then all lengths are always positive, obviously. Not so in relativity, where there are space-like, time-like, and light-like directions. But in ordinary geometry, all distances are always positive. So that means if you take a dx, let's, for space, let's just use m and n instead of mu and nu. Mu and nu will be reserved for space-time. dxm, dxn, gmn, mn of x. This must always be greater than 0, strictly greater than 0, as long as dx's are not, the dx's could be small, they don't have to be infinitesimal, just small. Think of them as just small little components of vectors. Every vector has a positive squared length. Square of any vector is always positive, and so this has to be greater than 0. Now, if you have a matrix which, when you multiply it on the left times a vector and on the right times the same vector, and it must be positive, then there's something you can say about that matrix. Does anybody know what it is?
Positive definite.
It's positive definite. And that means exactly what? Positive definite eigenvalues. So it means that the eigenvalues of GMN are positive. That's about all. That's about the only thing that that is required. And of course, if all the eigenvalues are positive, well, then all the eigenvalues are positive. Yeah. Any vector will have a positive squared length. So if you think of this as the squared length. Now, in relativity, let's go back to special relativity. In special relativity, d tau squared is equal to dt squared minus dx squared, minus dy squared minus dz squared, or whatever, in special relativity, for example. Now, if I want to put in the speed of light, I can put in the speed of light in one of two ways. I can either multiply this one by the square of the speed. I need to give these the same units. This has units of length squared. This has units of time squared. They're not compatible. To make them have the same units, I need some speeds of light. I can either put the speed of light squared here, but in that case, what is the units of this quantity? Well, let's just not worry about it for the moment. Let's just define, let's just erase this side for a minute and let's just consider this expression. What are its units? Length squared. All terms in it have units of length squared. That's a perfectly fine definition. Nothing wrong with it. But I just prefer, it's a pure personal preference, to define the proper time so that it has units of time. To give it units of time, we don't want to put a c squared here. We want to put the c squared in the denominator here. It's just the same quantity except divided by c squared, and I call that d tau squared. Now, obviously, I put back the speed of light, so later on when we throw away the speed of light, we'll just call this 1. But what was the question anyway?
What were the constraints on a matrix?
Yeah, okay, all right, right. So the speed of light is not the issue here, but quite obviously there are directions in which the tau squared is positive. There are, for example, the directions in which all the space components are 0 and there's only a time component, right? A time-like vector. There are directions in which d tau squared is negative, a pure space-like vector. So d tau squared, despite the notation as the square of something, is not really positive definite. Space-like vectors have negative d tau squared. Time-like vectors have positive tau squared. What about light-like vectors? Light-like vectors are vectors which have the property that d tau equals dx, for example, divided by c, or equivalently, dx equals c d tau. C dt. Those are vectors, and they're non-zero. The components are non-zero, dx and dt, but they correspond to light-like directions, and for them the proper time is just plain 0. So there are clearly directions in which this is not greater than 0. There's directions in which it's 0, and directions in which it's negative, and directions in which it's positive. All right? Looking at this matrix, looking at this here, we could write down the metric tensor. The metric tensor as a matrix would have a 1 and a -1 over c squared. Let's get rid of the c squared now. Now that I've put the c squared in, let's take it back out. -1, -1, -1. Okay? How many positive eigenvalues does it have? 1. How many negative eigenvalues? 3. The 3 negative eigenvalues correspond to the idea that there are 3 space directions, and the 1 positive eigenvalue corresponds to the idea that there's 1 time-like direction. The metric in relativity, general and special, must have the feature that there are 3 space-like directions, which means 3 negative eigenvalues and 1 positive. Now I should tell you that if you compare with much in the literature, depending on how old the literature is, depending on the tastes of the author, and depending on how quirky the author is, one sometimes defines, instead of the proper time, one defines a proper spatial interval, and one defines it this way: ds squared, s for space, and defines it as dx squared plus dy squared plus dz squared minus c squared dt squared. That's clearly the same thing, except for a factor of c squared and a negative sign. They are the same thing, and so far there's no difference between what I would write down and what everybody else would write down. D tau squared is the top thing, ds squared is the bottom thing, but sometimes the metric is read off this expression, in which case the metric would be 1, 1, 1, minus 1. Now, it's not that the physics is different, it's just the definition of what you mean by squared length is different. In one case, you think of squared length as being a time-like object, proper time. In the other case, you think of it as being a space-like object. And so depending on notation, there are many, many, many physicists who like the metric to be 1, 1, 1, minus 1. Okay. I use minus 1, 1, 1, 1. Why? I don't know. I guess it's because I am a maverick. And I warn you that that almost everybody uses the other notation. I think Einstein used the same as I did, but I don't remember.
You just wrote it as 1 minus 1 minus 1.
Sorry. Yeah, you might put the minus 1 up here and 1 down here. That doesn't matter. Right. So in one set of conventions, you would say that the eigenvalues are 3 positives for the 3 directions of space and 1 negative. In the other set of conventions, you would say 1 positive for time and 3 negative for space. The main thing is to be consistent. You can use either, whichever you like, but be consistent. Essentially, all the formulas are the same no matter which way you do it. You just have to remember in the end what you're doing. Right? It'll always come back to the special relativity description, which one you're doing. Are you talking about proper time, or are you talking about proper distance, proper space-like distance? Okay, so with that warning, again, I can't remember what the question was. The properties of the metric, yes. It can be anything at all within reason, smooth, differentiable, not always. Sometimes it's allowed to have certain singularities. But mostly you want it to be smooth, differentiable, like any other field.
Invertible.
Invertible.
Symmetric?
Symmetric.
It has to be locally Riemannian or pseudo-Riemannian.
Well, what does locally Riemannian mean?
And a local area, it has to be Minkowskian.
Locally Riemannian simply means it's smooth. Means that it's continuous and maybe differentiable, but even that's not necessary. Just that it's a smooth, a smooth metric. All right, let's write down the conditions. Let's write them down. Help me out because I don't remember. Smooth, which means continuous and differentiable. And you can differentiate it as many times as is necessary in a calculation. So just assume it's smooth enough to differentiate as many times as you need to. Smooth. Okay. What was next? Invertible. Now that, well, let's put in before invertible. Let's put symmetric. Let's put symmetric. Now, where did the symmetric come from, incidentally? Remember its definition. It's d tau squared equals g mu nu dx mu dx nu. What would happen if there was an anti-symmetric piece to g mu nu? Any matrix can be written as a sum of symmetric and anti-symmetric. The anti-symmetric means that when you interchange the indices, it changes sign. What would happen if g mu nu was anti-symmetric? You would get 0 from this. You would get 0 from this because the coefficient, for example, of dx1, dx2 would be opposite to the coefficient of dx2, dx1. But they're the same thing, the product dx1 and dx2. So if it was anti-symmetric, you wouldn't get anything. Any matrix can be written as a sum of symmetric and anti-symmetric. Only the symmetric part of g mu nu will contribute. So you might as well say that g mu nu is symmetric. All right. Now, any matrix, yes?
Is the requirement to be symmetric just for convenience?
Well, let's put it this way. Any terms that you would put in that were anti-symmetric wouldn't affect anything, so they would be sort of spurious, no physics to them. Nothing could determine them since they're arbitrary. So yes, it is a question of convenience. Yes, yes, it is a question of convenience. Absolutely. But once it's symmetric, then you can say that it has eigenvalues. And how many eigenvalues does it have? in general, it will have a full set of eigenvalues equal to the dimensionality of a space. So there will be, for example, in four-dimensional space-time, 4 eigenvalues. So it will have, by virtue of it being symmetric, it will have a set of eigenvalues. What is the condition that the matrix be invertible? Non-zero determinant, but that simply means no zero eigenvalues. All right, because the determinant is just the product of the eigenvalues. So, invertible simply precludes 0 eigenvalues. Eigenvalues which are 0. That's all this means. Once it's symmetric, it's invertible. But then on top of that, it should have, depending on the application, if we're talking about ordinary space versus space-time, in ordinary space, it should have all positive eigenvalues. And of course, we would be talking about ds squared then, not the tau squared in ordinary space. All positive eigenvalues. And one would say the language that mathematicians use is they would say the signature of the space would be plus, plus, plus. Plus, plus, plus is the signature of the space, and it's simply telling you how many positive and negative eigenvalues. If I use this notation here, where I study the proper time, I would say that the signature of the metric was minus, plus, plus, plus. 1 minus and 3 pluses. So for the purposes of general relativity, or relativity in general, the signature of the metric is plus, minus, minus, minus. In other words, this means 3 negative eigenvalues and 1 positive eigenvalue. Those are the conditions for a metric to be an allowable metric.
Symmetric guarantees that the eigenvalues are real.
Ah, good. Yes, but not positive. Right, absolutely. Okay, so that's the conditions on a metric. Now, there are important dynamical conditions. For example, the gravitational field is the metric. It's the thing which satisfies equations of motion. How do I know that my equations of motion won't suddenly, at some point in time, change the signature of the for example, how do I know that some g mu nu, let's say 1 minus 1, oh, sorry, 1 minus 1 minus 1 minus 1, won't evolve in time and eventually become 1, 1, minus 1, minus 1. That better not happen. This is not an allowable metric to describe a sensible space-time. 2 space directions and 2 time directions, bad news. That's not a good thing. Why doesn't that happen? What is the dynamics? What is it in the equations of the theory, in the evolutionary equations of the theory, which tells things how to change from moment to moment, which precludes this from happening? Well, I can tell you one thing. What's the determinant of a metric with 1, minus 1, minus 1, minus 1? These are the eigenvalues. I'm specifying the eigenvalues. What's the determinant of the metric here? Minus 1. What's the determinant of the metric here? Plus 1. Somewheres, the metric will have had to go through having determinant 0. So if there's something in the dynamics that forbids determinant going to 0, some sort of effect in the energy or somehow in the dynamics which pushes you away from determinant 0, some dynamics which repels the metric away from determinant 0, then it can't change signature. And of course, in general relativity, there is such an effect. Passing through 0 would cost infinite amounts of energy, and so it doesn't happen. Or if it does happen, it's extremely pathological. I don't know any case where it happens. Okay, so that's those were good questions. Now we come to Einstein's equations and so forth. But before we do, question.
Can it change signature without changing sign?
No.
Without the determinant changing.
There's no way that you can go from a positive determinant to a negative determinant smoothly. Remember, the metric is smooth. So supposing in this point over here in space-time, the determinant of the metric, incidentally, the determinant of the metric is usually just called G, like that. It's the product of the eigenvalues. All right? Supposing the determinant of the metric over here was minus. In other words, supposing the signature was 1 minus 1 minus 1 minus 1. And then it wants to make a transition at some other place over here. It's going to have the opposite metric, the opposite determinant. Here it's positive, or negative, sorry, negative. Here it's positive. Well, here's some curve, smooth curve between them. Someplace, if the metric is smooth, it's going to have to go to 0. And those are the kind of places where the equations push you away from those places. And that's generally true, that it's generally true that the equations push you away from places where the signature of the metric might change on you. So that's a good thing. Space-time cannot change into space. Space-time cannot suddenly become 4 dimensions of space. That would be very awkward. Nor can it suddenly become 2 dimensions of time and 2 dimensions of space. There are dynamics which prevent that from happening. Okay. Let's come to seeing what we can learn about, as much as possible that we can learn, about the equations of motion, the field equations of general relativity. We're not going to go through the whole business. The whole business is a bit tedious, but I'll tell you the important facts.
Does something happen to the determinant when you fall through a black hole event horizon?
No. Nothing happens to the determinant when you fall through a black hole. We may or may not get to that tonight, but no. Now, something happens at the singularity of a black hole. Expect everything to get nasty, and all bets are off when you come to places like singularities of black holes. It's not that the metric changes signature from space to time or something like that. Just the smoothness breaks down, and components of the metric, curvatures become infinite, bad things happen. But those are the exceptional cases, which are, of course, the subject of black holes and singularity theorems and things of that nature. Okay. And it's not that they're irrelevant. They're quite relevant, but for the moment, let's say temporarily, let's just ignore, or not ignore, but let's pretend that there are no singularities. All right, let's talk about begin with what we want to compare is Newton, we've done this in various situations, with some ideas from Einstein, and try to put together or try to guess the equations, the tensor equations that replace the Newtonian equations. To do so, if we're going to think about the Newtonian equations are the Einstein equations in certain limits. There are certain limits where certain things are big and other things are small. Let's see if we can figure out what things are likely to be big and what things are likely to be small, and then systematically think of non-relativistic limit as the limit in which small things are really much smaller than big things. And of course, what we're talking about mainly being small is velocities. Velocities on the one hand, and also the strength of gravitational fields. The strength of gravitational fields should not be too big, That entails saying either that no object in your theory is so compact and so compressed that, that the acceleration due to gravity becomes enormous, or it can just mean stay away from such objects, stay far away from such objects, which of course are black holes. But slowly moving things with relatively weak gravitational fields are the subject of Newton. All right. Well, first of all, the first thing to say is that the metric under such circumstances, in a frame of reference where everything is moving slowly, is close to the ordinary non-relativistic metric. That means that apart from small quantities, G naught naught is 1, and I'm going to write 1 plus small. And we're going to keep track of small things, all right, but we're going to keep track of them to the leading order, basically. All right. It also means that, what about G11? Well, that's equal to -1 plus small things. What about G22? Same thing. What about G01? Well, that's something that does not appear in ordinary special relativity. And so if we're, when I say, I should say, when I say that, that there are two limits, both of which we should keep track of. One of them is things moving very, very slowly, in which case Newton, weak fields and slowly, then Newton is the right physics. What about weak fields, but you move fast? Special relativity. All right. So we want to deal with both of those. But in special relativity, G01, what is G01? That's 0. That's not there in special relativity. Where's special relativity? Here's special relativity, and there are no terms multiplying dt by dx. Oh, this is equal to 0. Plus small things. We can write this, we can generalize this. Gmn, I'm not going to write the Kronecker delta, I'm just going to write that G11 equals G22 equals G33 equals, and so forth. And G12 equals blah, 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 blah equals 0. Now, I don't literally mean this, that they're literally equal to 0. I mean they're equal to 0 plus small. Plus small. We will keep track of small things, but the first approximation is just special relativity. Now, next, let's concentrate on energy and momentum. We're going to be dealing with the energy-momentum tensor, and the energy-momentum tensor is essentially the right-hand side of Einstein's equations. It's the sources of the gravitational field. Energy, of course, is the same as mass through the E equals mc squared relationship. Mass is the source of gravitational field, and so energy is the source of gravitational field. But since we're forced to write tensor equations, in some frame of reference we may have an energy, in some other frame of reference that same energy turns into energy and momentum. In a frame of reference where there's some energy, if we move past that energy, that means there's some mass there. If we move past that energy, then of course we see some momentum. So momentum and energy go together, and if we're going to be writing tensor equations, we should expect on the right-hand side of those equations, some of the equations will have momentum in them as sources of the gravitational field. In other words, the energy-momentum tensor is the important thing. But which components of the energy-momentum tensor are likely to be big and small in the slow weak field limit? So let's begin with the ordinary energy of a particle. What's the energy of a particle of mass m in free space? mv squared over 2, good. 1/2 mv squared over 2? No, just 1/2 mv squared. And remember, v is small. What's the momentum? mv. This is energy. This is momentum. Momentum, this is p, mv. All right, v is small. Remember that v is small. So which one of these is bigger? mv, right? Yeah, it is true. mv is bigger than mv squared. But we forgot a term here. mc squared. Right? Every object of mass m has an energy mc squared. C is bigger than anything in sight. M times, let's write this as m times c times c. Well, mc is certainly bigger than mv, because c is big, 3 times 10 to the 8th meters per second. No, 3 times 10 to the 8th meters per second. And c is doubly big here. So this is typically much bigger than mv. The biggest thing around in terms of energy and momentum for a massive object, you know, for a star or for a thing which gravitates, the big term in the energy momentum tensor is the energy density. All of the other terms are much smaller because they don't have the mc squared energy.
How can you compare things with different units?
This has the same units as this. Oh, you mean compare it with momentum?
Yeah.
Well, okay. We can work. What we can do is work in units where the speed of light is 1. Okay. Then they will have the same units. Okay. If we work in units with one of them is m. That means velocities have units of no units.
Okay.
Right. So the right statement is in a dimensionless sense, namely the sense in which we choose the speed of light to be equal to 1. Typically, momenta are much smaller than energies. Energies have this big whopping mc squared term, and momenta. The other way to say it, we can either say it mc squared is big because c is big, and this doesn't have any c in it. The other way to say it is that in units in which c is equal to 1, we have an energy which is m, but then we have a momentum which is terribly small because the velocity is small. Okay, comes to the same thing. Sometimes it's fun to keep track of the speeds of light just to see what's big and what's small. Okay, meaning of this is that the first approximation for a gravitating object, for the source of a gravitational field, if that object is at rest, or not moving, at rest means moving slowly compared to the speed of light, then the energy momentum tensor really only has one significant component, T0, the energy density. The momentum, the energy flux, the object's not moving very fast. The energy flux will be small. The momentum density will be small. The flux of momentum will be small. Everything is small except T0. And what is T0? T0 is the energy density. Now I will keep reminding you, energy density and mass density are the same thing if I choose the speed of light equal to 1. So, to the first approximation, the big chunk in the energy momentum tensor is just the mass density and everything else being 0. Plus small. Okay, so that's something we should keep in mind when we're trying to compare with known physics, so to speak. I mean, what was Einstein's situation? He had these geometric ideas. He thought gravity had to do with the metric of space-time, but he needed some equations. The first thing to do was to make sure that in the limit where Newton ought to apply, or in the limit where special relativity ought to apply, that they do apply. So that was the first test, if you like, or the first criteria, a principle of correspondence with known physics. Okay, that's second. Metric, basically special relativity. If we keep track of the speeds of light, then actually the only big component of the metric is the time-time component. The space components are smaller by a factor of 1 over c squared if we keep track of the speed of light. Okay, if we keep track of c in the equations. And it's useful sometimes to keep track of the speed of light. Okay, what else do we know? We know from Newton, or generalized Newton, Newton plus Gauss plus whoever else was involved. We have a field equation that the gravitational potential satisfies del squared phi is equal to 4 pi g rho. This is a disguised form of the inverse square law. Okay. And we also found out by looking at the motion of geodesics, slowly moving particles satisfy the usual acceleration acceleration is equal to minus the derivative of the, what is the usual equation? Acceleration is equal to minus the gradient of phi, or minus the ith component or the mth component of the acceleration is equal to the derivative with respect to m of phi. Is it minus or plus? Minus, I think. That's F equals ma, except dividing by m. Acceleration is the gradient of the potential. Okay, so we have that. And if we compare that with the equations of a geodesic, that tells us the relationship between the gravitational potential and a certain component of the metric. Remember, we worked that out. For slowly moving geodesics, we found that, what was it? Anybody remember the formula? I'm trying to, I have things written down, but I'm not sure they're right. Yeah, I think they are right. What we found out, well, was that the gravitational potential was like 1/2 of g naught naught. Now that's not right. That's not correct. That's not correct. What actually did we find out?
G naught naught is 2 feet.
Yeah, plus c.
Plus a constant. What we really found out is that the derivatives of phi were related to the derivatives of g. Where did the derivatives of g come from? They came from the Christoffel symbols. Only in the equation of motion, F equals ma, only derivatives of phi appear, and in the Christoffel symbols, only derivatives of g appear. So it was really that the derivative of phi in any direction is the derivative of g naught naught, but another way to write that is that phi is equal to g naught naught plus some constant which doesn't vary in position. Now again, I emphasize, is it g naught naught is equal to phi, 2 phi?
Yeah, G naught naught is equal to 2 phi.
Or is it minus? This sign drives me crazy. I believe it's plus.
Do you want to use C or do you want to use K or something?
Yeah, I do not want to use C. Thank you. Let's call it CONST. Constant. Of course, the speed of light is also a constant, but I think that I don't think it'd be unclear. Good. Okay.
The first equation on this board says the gradient of the potential, the del squared of the potential at any point in space is equal to the density of mass at that point in space.
Yes.
So if there's no mass, the potential isn't changing? Is that
No, it doesn't say that it doesn't, no, be careful, be careful, be careful. Good, that is a good question. What is this thing here? It's the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. All right? What it says is that some are positive and some are negative. It doesn't say that each one of these is 0. First of all, even if it said that each one was 0, it wouldn't say it was constant. It would still allow a first derivative, but that would be rather limited, just having first derivatives. What it says is that the combination of these second derivatives have to add up to 0. That's quite a different thing than saying it is that they are individually 0. So no, the gravitational potential does vary from place to place. For example, if you take the gravitational potential 1 over r, 1 over distance from the origin, then except at the origin itself, if you work this out, you will find out that del squared of 1 over r is equal to 0. So that is a good question, and it has a good answer, the answer being that it does not say that the individual derivatives are 0, but just a combination. So at any point in space where there is no matter, this combination adds up to 0. But there are plenty of functions with that property. Let's write down some functions with that. Let me just write down one function with that property. Take x squared plus y squared minus 2z squared. Okay. What's the second derivative? I'll call this phi. What's the second derivative of this with respect to x? 2. How about with respect to y? How about with respect to z? Minus 4. So 2 plus minus 4 is equal to 0. Okay, so this is a question. This is a function. Functions with this property are called harmonic functions. There's lots of them. There's no lack of harmonic functions, but there's still not as many as there are of all functions, so there are restrictions. Okay, now, what is this object on the right-hand side? We clearly have something involving T naught naught, right? The gravitation, the mass density. On the left-hand side, we have something involving two derivatives of what is in essence G naught naught, components of the metric. We don't have to worry about this constant. The first derivative gets rid of the constant, and the second derivative gives us some second derivative of G naught naught. So what's on the left-hand side involves second derivatives of G naught naught. There are not a lot of tensors that are made up out of the second derivatives of G naught naught. There are relatively few of them, basically only 2 geometric tensors that are made up out of G naught naught. What we actually want to have on the right-hand side is T mu nu. In the generalized equation, I'm not saying that this is equal to this. I'm saying the more general equation that we would like to be the tensor analog of this will have the energy momentum tensor on the right-hand side, maybe some 4 pi g, maybe some constant. Let's call it k for constant. All right. And on the left-hand side, we need some tensor with 2 indices, which is made up out of the second derivatives of the metric. Second derivatives of the metric, that should ring a bell. Sounds like the curvature tensor. It can't be the Riemann tensor because that has 4 indices. It can be the Ricci tensor. The first thing that Einstein tried was just r mu nu equal that, okay? He ran into grief. And the reason that he ran into grief had to do with energy momentum conservation. Let's write down what in ordinary I suppose special relativity, the conservation of energy momentum, let me just remind you, go slow. The conservation of charge. The conservation of charge was expressed in terms of a current, and the current had an index mu. The time component was density, the space component was the flow of charge, And anybody remember what the equation is for continuity equation? Or just derivative, ordinary derivative. It can also be expressed in terms of a covariant derivative. But an ordinary, an ordinary flat special relativity, it's d mu j mu is equal to 0. Also in special relativity, there's a conservation of energy and momentum. Each component of the energy and the momentum are conserved, and that became the equation d mu of T mu nu is equal to 0. Nu here tells you whether you're talking about energy and momentum. Mu tells you whether you're talking about the density or the flow. And so for each nu, this is a continuity equation. The correct continuity equation, and we'll come to this, I'll explain the difference in a little while, but the correct continuity equation is that in this form, it doesn't really make sense. Why not? Because it's not a covariant derivative. Incidentally, we're going to have to come back to why this one does make sense. But let's just focus on the energy momentum tensor. The right equation is this one. That the covariant, that's a nice tensor equation. If it's true in one frame, it's true in every frame. Covariant derivative of T mu nu is equal to 0. For the charge density, the covariant derivative and the ordinary derivative can be taken to be the same for technical reasons that I may or may not ever get to, but let's concentrate on the energy momentum tensor. It should satisfy del mu, T mu nu equals 0. That should be a property of the energy momentum tensor. Without it, there would be no conservation of energy. We must have, in special relativity, and in general relativity, we also expect some kind of local flow of energy and momentum. We expect it to be conserved. We don't expect energy to disappear and reappear in distant places. And so that says that a certain covariant derivative of T mu nu is equal to 0. We can try that out over here. On the right-hand side, we can take del mu of T mu nu times kappa, times k, times this constant k. And according to this equation, it would say that del mu of R mu nu is equal to 0. In other words, conservation of energy momentum would demand that this property be true of the Ricci tensor. Well, it turns out that that property of the Ricci tensor is almost never true. Basically, it would require, it's just a property of the Ricci tensor. It's never true. It's a false theorem or a false identity. What Einstein wanted was for the left-hand side to be an identity, automatic, so that energy momentum so that energy momentum conservation would be a consequence of his equations. He wanted to follow the pattern of Maxwell's equations. Maxwell's equations have the property that they're connections between the electric and magnetic fields on one side, something involving E and B on one side, whatever it is. And on the other side, what's on the other side? The charge density and the current. Well, Maxwell's equations have the property that whatever is on the left-hand side automatically as an identity, in other words, for every electric and magnetic field that you can write down, that you can build up out of the vector potential, that the derivative is automatically 0. And so what you can say about Maxwell's equations is that charge conservation follows from the form of Maxwell's equations. It's not something you have to add to Maxwell's equations. It follows from Maxwell's equations. Einstein wanted the same pattern. He wanted energy and momentum conservation to be an automatic consequence of his field equations. And for that, he would have had to have that del mu r mu nu, the covariant gradient of r mu nu, covariant divergence of r mu nu, should be 0 for every r mu nu. But it just isn't true. You take a general differential geometry and you calculate let's call this the covariant divergence of r mu nu. It's not equal to 0. When you calculated it, how do you calculate it? You put in for r mu nu its expression in terms of the Christoffel symbols, and then actually I think that's all you need. I don't think you even really need to write the Christoffel symbols in terms of the metric, but you use the expression for r mu nu in terms of the Christoffel symbols. You know what covariant derivative means. It means ordinary derivative plus a thing with some Christoffel symbols, and you simply work it out. And what you find is, let's see if I can find it. Damn it. Yeah. Here's the identity that you find. You find that del mu of r mu nu is not equal to 0. It happens to be equal to 1/2 g mu nu times the derivative with respect to mu of the scalar curvature. Everybody remember what the scalar curvature is? There was the Riemann curvature, the Ricci curvature, which you got by contracting two indices, it left over two indices, and the curvature scalar you got by contracting the remaining indices of the Ricci tensor. That's what he found. Now, I don't know for how long that puzzled him. I don't know how long it took him to put 2 and 2 together. But after a while, he realized the following facts. First of all, the Riemann curvature, the curvature scalar here is a scalar. What's the covariant derivative of a scalar? No, it's not 0. It's just the ordinary derivative, the partial derivative. Yeah, the ordinary partial derivative. So this could be replaced by covariant derivative. Now, covariant derivatives are a little bit strange, but they satisfy the usual rules that the covariant derivative of a product could be product of any tensors. I'm not even going to write indices for them. Any two tensors, A and B, satisfy the usual rules. A times the covariant derivative of B plus the covariant derivative of A times B. Covariant derivatives do have that property. At least they have that property. So now we look at this over here, number 1, and we say, wait a minute. Remember the fact that the covariant derivative of the metric tensor is 0. The covariant derivative of the metric tensor with upper or lower, it doesn't matter. It doesn't matter where you put the indices. The covariant derivative of the metric tensor is 0. So you can also write this as 1/2 the covariant derivative of g mu nu times r. Why is that? Well, this contains g mu nu times the covariant derivative of r, but it also contains r times the covariant derivative of g mu nu, the last term being 0. So he discovered del mu nu of r mu nu is equal to 1/2 del mu nu of g mu nu r. Now, I don't know if this was known before Einstein or not. I don't know that anybody ever had any particular reason to calculate the covariant derivative of r mu nu, the covariant divergence like that. And how many weeks, months, days, hours, or seconds it took for Einstein to say, hey, wait a minute, I can now take this over to the left-hand side and write that this is equal to del mu times r mu nu minus 1/2 g mu nu r is equal to 0. That was the big breakthrough. That was the big breakthrough, realizing that there was, in fact, is and was, in fact, a certain tensor that can be made up out of the Ricci tensor and the Ricci scalar times g mu nu, which has automatically, for any metric, doesn't matter what the metric is, for any metric whatever, the del mu of this tensor here is automatically 0. It's an identity. If you plug in for r mu nu its expression in terms of the Christoffel symbols, you'll find this to be true. Okay. And again, I emphasize, you don't need to put in any special form for the metric. Only important thing is that it be differentiable enough to be able to do all the derivatives. Other than that, it will always be equal to 0. So that, first of all, Einstein gave this a name. Very modestly, he called it the Einstein tensor. I don't know who called it it wasn't Einstein. He could have called it E mu nu, but he didn't. He called it G mu nu. No, sorry. Yeah, del mu, G mu nu equals 0. G mu nu is just the Ricci tensor minus a half G mu nu times the curvature scalar. Once he realized this, he knew what he had to do next. What he had to do next was replace this inconsistent equation. It was inconsistent, at least it was inconsistent with energy momentum conservation. He replaced it by...
Is there some reason why we don't put the constant in front of g mu nu?
The what?
The scalar in front of g mu nu?
The scalar in front of
Ricci
g mu
scalar.
nu. You mean make it r times g mu nu?
Yeah.
No reason whatever. No reason whatever.
So these are actually 4 equations, the bottom one?
4 equations, yes. 4 equations. Yes, 4 continuity equations. These are not the field equations of Einstein. The field equations are the other ones over here. These are the continuity equations for energy momentum. There's a continuity equation for energy. There's a continuity equation for the x component of momentum, another one for the y component, another one for the z component, and so forth. 4 distinct equations that express the local continuity of energy and momentum. Right. And they are the closest thing that there is to energy momentum conservation in gravity. Now, there's a certain point that I'm going to come to that's a little bit subtle about why they don't express conservation in the usual sense, but we'll come to it soon. And we shouldn't expect it to, but let's go. We'll come to it soon enough. All right, so Einstein said, nope, let's put G mu nu here. R mu nu minus 1/2 G mu nu, oh sorry, R mu nu with an upstairs index. And there we are.
The left side is symmetric, so this energy momentum tensor is symmetric.
It will tell you that the energy momentum tensor is symmetric. Yeah. Now, I haven't gone into the question of the symmetry of the energy momentum tensor. The symmetry of the energy momentum tensor is required by Lorentz invariance, and I think it would just take us outside the scope of these lectures. But what one can say is that the Einstein equations require T mu nu to be symmetric. So just as it requires T mu nu to be conserved, it also requires it to be symmetric. And if you look at the energy momentum tensor for any kind of reasonable field theory, it's always symmetric. So one can say this is the reason why. Yeah.
I'm a little confused. Is that a condition on the sum, or is that saying the
no, individual components. Component, but it's a tensor equation. A tensor, the sum of what? There's nothing to sum here. There's no repeated indices in these equations. Oh, you mean the sum of this and this? Sum of what?
And the T mu there on the other side.
Sorry? Sum of what? You can't say the sum of and T mu nu on the other side. The sum of what and what.
R01?
No. This is 16 equations. 4 times 4, 16 independent equations. So there are 16 Einstein. Now, they're not all completely independent. There are relationships among them. But at first sight, and without being too subtle, these are the 16 independent Einstein equations. Just like Maxwell's equations, how many Maxwell's equations are there? Let's see, del dot, 1, 2, 8 Maxwell equations. There are 16 Einstein equations, right, for the various components of the gravitational field.
Last week you said that the Riemann tensor, in 4 dimensions, the Riemann tensor doesn't have to be 0 for the Ricci tensor to be 0.
That's correct.
Okay. And if the Ricci tensor is 0, then the scalar is 0.
Say it again.
If the Riemann tensor is 0, then the curvature scalar is 0. That's just a contraction of that.
If the Ricci tensor is 0, that's right.
So that means that the stress energy, that the energy momentum tensor is 0 in that case. So you have energy momentum tensor is 0, but you don't have flat space, right?
Yeah, okay. Let's go through the cases. First possibility is the energy. Let's take the case where the energy momentum tensor is 0. Okay? Energy momentum, no energy momentum, whatever. Then the right-hand side is 0. Let's see what we can say. That says that r mu nu minus 1/2 g mu nu r is equal to 0. So far, it's not obvious that it says that r mu nu is 0, but it does, which I think is what you were getting at.
I was actually going, if r mu nu is 0, then, then you'd have no energy, but you'd have curved space instead of seeing.
Yeah, well, yes, what you're saying is correct, but let me just say it in its general form. Take this equation here and contract it with g mu nu lower index. Okay. What is the contraction of g mu nu with r mu nu? R, just the scalar r. So what this is then is it's r minus 1/2. And what is the contraction of g mu nu with g mu nu? Whoa, not quite. We were summing over both indices. Okay, good. Let's do it. Let's work it out. Okay. I want g mu nu times g mu nu, right? So let's back off for a moment and do something a little simpler. Let's take g alpha nu g nu mu. What is that? That's the Kronecker delta. That's the Kronecker delta, delta alpha mu. But now I want to identify alpha with mu also, because that's what I have here. G mu nu, G mu nu. So what happens if I identify alpha with mu? Then this becomes mu, and this becomes mu also. What is delta mu mu? No? No? I heard 1, I heard 2, I heard 4. 4 is, of course, the right answer. Why? Because it's the sum of the 4 components. It's the 1, 1 component plus the 2, 2 component plus the 3, 3 component plus the 4, 4 component. So this number is 4. And a nice thing to remember. Delta mu mu, remember it's summed, is 4. So let's see what we have here. And we now have minus 1/2 times 4 times r. Minus 1/2 times 4, if I remember correctly, is minus 2. So this is minus 2 times r is equal to 0. In other words, minus r is equal to 0, which means plus r is equal to 0. R is equal to 0. Now this is, remember what this is. This is the case where there is no energy momentum. So first of all, it says that the curvature scalar is equal to 0. if there's no energy momentum around, the curvature scalar is equal to 0. This is kind of like del squared phi equals 0. Doesn't mean that the metric is trivial. It just says some particular thing is 0 about the metric. But if r is equal to 0, let's come back now to the original equation before we contracted it. If r is equal to 0, then we can also say that r mu nu is equal to 0. So the right statement is that in regions of space and time where there is no energy and momentum, the Ricci tensor is equal to 0. Now, what does that say? In three-dimensional space or two-dimensional space, the Ricci tensor being 0 would say the space is flat. In four-dimensional space-time, the Ricci tensor being 0 is not enough to tell you the space-time is flat. There are too many components, too many independent components. What kind of things can you imagine can be going on? Let's imagine a space-time which is completely empty of matter, meaning mass, meaning right-hand side. A space-time which is everywhere completely empty. Does that mean that it's flat? No, it means that the Ricci tensor is everywhere 0. Are there geometries which have Ricci tensor equal to 0 everywhere but aren't flat? Yes, indeed, there are. Anybody have an idea what those geometries correspond to? What's that? No. These are geometries with a signature plus, 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 minus. I mean, the usual, good space-time. Oh yes, of course. No. Geometries which are not flat. Euclidean geometry is flat. Are there geometries, or what might they correspond to physically? Gravitational waves. Just gravitational waves moving by. Waves, wave-like disturbances of space-time, which are not trivial. For example, there are plane wave gravitational excitations in which the various components of the metric wobble and wiggle, but where the Ricci tensor is everywhere 0, but the Riemann tensor is not. So there are solutions, empty, or they're usually called vacuum solutions. They're called vacuum solutions because they don't contain any ordinary energy and momentum, but they do contain gravitational waves. Disturbances, real disturbances. Yes. Okay. That's a good. That is a very interesting point. So let's come to it right now. Let's face it head on. Here's our equation of energy momentum conservation. Del mu T mu nu is equal to 0. This is not the same thing as d mu T mu nu is equal to 0. This equation is the ordinary continuity equation, and it's the equation which expresses the idea that if you have a region of space, the change of quantity, for example, charge, if this were d mu, j mu is equal to 0. This kind of equation here expresses the idea that if the charge changes inside a region, then the only way it can do so is by flowing outside. This equation is different. It has an extra term in it. There's a d mu T mu nu, plus another term with some gammas and so forth. What's going on here is that this here is the energy and momentum of everything except for the gravitational waves. It's the right-hand source term which expresses the sources of the gravitational field, but it does not contain the energy and the momentum in the gravitational field. That And that's why, by itself, you don't have energy conservation in general relativity. In general relativity, if you take only the energy that appears on the right-hand side of the equation, it's not conserved. Why? Because the gravitational field also has energy and momentum. It's different than electrodynamics. In electrodynamics, charge is the source of the electric and magnetic fields. The electric and magnetic fields do not have charge. They are completely uncharged. So if electric charge is conserved, it's because the electric charge of things like electrons and protons and neutrons is conserved, and you don't have to worry about the electric charge of electromagnetic waves. There is none. But in gravitational theory, the wave-like disturbances of the gravitational field themselves carry energy and momentum. And therefore, energy and momentum is more complicated. Some of it comes from ordinary stuff, and some of it comes from these gravitational waves. We'll come back to this.
Question?
Yeah.
Regarding the gravitational waves, does that discussion pertain to, let's say, a universe that has no mass or energy in it, but somehow has gravitational waves, and therefore those...
A universe that has nothing but gravitational waves, has no T mu nu on the right-hand side. It does have these wave-like disturbances. The wave-like disturbances do have energy and momentum. So effectively, this cannot be the whole energy and momentum. Right? Einstein understood that. There's another thing you can write down, which is the total energy and momentum. But the thing that goes on the right-hand side is not the whole total energy momentum. It's almost as if it's analogous to a situation which would exist if photons or electric and magnetic fields had charge. Then the charge of ordinary charges, ordinary I now mean protons, electrons, and so forth, they would be the sources of the electromagnetic field. But the electromagnetic field, when it was radiated off, would carry off charge if photons were charged. And so the electrons plus the protons by themselves would not have a conserved charge. In fact, you could even say more. You could even say, well, if the photons themselves are charged, they are sources of their own selves. When a photon is accelerated, it could bounce off a mirror. It should emit some more photons. That's the way gravity is. Gravity is a field which is sourced by energy momentum, but it also carries energy momentum, not on the right-hand side of this equation, but other pieces of energy momentum, so that when gravitons are accelerated, they will emit other gravitons. So it's a more complicated kind of story. It's nonlinear. All right, we'll discuss this again. But let's see now what we can learn. We have a guess now. This was Einstein's guess for the gravitational field equations. The hardest part of this little exercise is to show this identity here. I know two ways to do it. One of which is a one-line proof, but it requires very sophisticated stuff, which we don't have. And the other is a many-line proof, which is mechanical, straightforward. I won't say mindless. That's not right. But in which you simply plug in for the components of the tensors, their expression in terms of the Christoffel symbols, and just check out that this relationship is true. Okay. Only way I know how to do it, other than to use a fancy, sophisticated argument. I started to do it, and by the time this is when I fell asleep. And I can assure you, if I were to do it on the blackboard, you would fall asleep. So I won't. But it's an exercise you do yourself, look it up, or just believe it. Okay. All right, so now let's see what more we can learn.
Is there a name for the fancy, sophisticated math?
Yes, variational principle. I'll tell you, all right, if you want to know, I'll tell you what it comes from. There is an action formulation of the general theory of relativity. Maybe we'll get to it. And what it says is the action is stationary with respect to variation of all the fields, in particular, stationary with respect to the variation of g mu nu itself. And it turns out that the variation of the action with respect to g mu nu is basically the Einstein tensor. So yeah, there's a fancy way to do it, but there's also a non-fancy way to do it. Nobody that I know of, I've asked a lot of people. I mean, I'm not an expert at general relativity, meaning to say, you know, I'm not an expert at the technology of solving the equations and stuff. There are people who are very, very good at it. They know a lot of fancy techniques, technology. I've asked them, do you have a simple geometric understanding of the Einstein tensor? Or even the Ricci tensor itself? And generally speaking, the answer is no. No, don't say anything especially simple and especially geometric about it. It just happens to be the thing that satisfies this identity. And I have never been able to find anybody who could reduce this equation to a simple explanation other than the fancy variation.
I think that applies to Francis Everett as well. He was asked a similar question about the frame dragging terms and gave...
Oh, wait, say again?
Francis Everett says basically the same thing, asked about the frame dragging terms. Is there a simple geometric explanation? He basically said no.
Well, that I would have to think about a little more. I think I could probably go a little better than that for the frame dragging. But this very particular equation here, I don't know. And Einstein himself just hunted around until he found the right thing. I wish I had a simple explanation for it. I never could find one, and I never knew anybody who knew one. And the worst part of it is it's not a lot of fun to check. It's rather tedious, but it's true. Okay, so let's see where we're going.
Just a quick question.
Yeah.
And again, this is not really an answer to your thing, but the way I see this stuff is special relativity is basically, stuff on a flat geometry. Right. Einstein figured out he can curve it. That models gravity and therefore acceleration. Curvature is a Riemann vector. That doesn't fit because there's too many components, so he shrunk it down to a Ricci vector. Now, what I'm seeing with this gravitational wave is that there's a difference in information between a tensor with 4 components and one with 2 components. The Riemann vector, the tensor around
there's more information in the 4 components than
and that information that's missing is being manifested in the form of gravitational waves.
Yes.
Is that an accurate?
Yes, that's absolutely correct. Now, in 3 dimensions, let's remember for a moment what the Riemann tensor is. The Riemann tensor has to do basically with 2 distinct rotations. One of the rotations, or 2 axes. One axis is you parallel transport around that axis. The result of parallelly transporting something around that axis is a rotation of that something about some other axis. So when you go around that axis with your gyroscope, the gyroscope gets rotated about some other axis. So it has to do with 2 axes, all right, in 3-dimensional space. In 3-dimensional space, rotations have to do with axes in space. That's not true in 4 dimensions. In 4 dimensions, they have to do with planes. In fact, they always have to do with planes. It's just in 3 dimensions, there's a correspondence between vectors and planes. Namely, every plane has the perpendicular vector associated with it. So, if the Riemann tensor has to do with pairs of rotations, pairs of rotational planes, then in 3 spatial dimensions, it can be thought of as having to do with pairs of axes. Pairs of axes, an axis is a vector. Right, if it has to do with pairs of axes, it means really it can be represented as something with only 2 indices. In general, it requires 4 indices, but Let me tell you another reason, another way to explain it. Supposing something has a 1-2 index in 3 dimensions. Supposing we're in 3 dimensions. Supposing something has a 1-2 index. Then I can just use a new notation in which I call it a 3 index. 1, 2 replaced by 3. 2, 3 replaced by 1. Pairs can be replaced by single indices in terms of information content, so to speak. So a plane has associated with it a vector. That's the same as saying 2 indices can be replaced by a 3rd index. The other 1, 1, 2 gets replaced by 3, 2, 3 gets replaced by, you know what I mean. Okay, so the answer is in 3-dimensional space, or even 3-dimensional space-time, if there was such a thing, the Ricci tensor would be a full description, and if the Ricci tensor was 0, the space is really flat. Okay? There is no other information, and therefore in a world of 2 plus 1, 2 space, 1 time, 3 dimensions, there are no gravitational waves. Any place in space where there is no material, no energy and momentum of this type, space-time is flat. Not just Ricci flat. Ricci flat is the statement that the Ricci tensor is 0, but just plain flat. No gravitational waves. In 4 dimensions, by the time you get up to 4 dimensions, then the Ricci tensor is not a full description of the geometry, though the Ricci tensor being 0 is not enough to tell you that all, whatever the number of components of the Riemann tensor are, is 0. And so there's some leftover information. That leftover information is physically in the form of the gravitational waves. Okay? So that's the story. Okay. Let's see how we're doing. We still have a few minutes. I'm going to try to leave a little early tonight because I have a very early morning flight tomorrow. There's a trick to rewrite this equation in another form. It's a kind of neat form in which it is an equation where r mu nu is set equal to something else. To see how it works, I'm going to show you how it works. Again, take this equation, not this one, but the full equation, and contract it with g mu nu. Contract it with g mu nu, what do you get? On the left-hand side, from the first term, you just get the scalar r. The second term, remember what this was? Minus 2r. Minus 2r. So that gives you altogether minus r. I'm running out of ink. Minus r. And on the right-hand side, you get k times g mu nu T mu nu. That's some scalar. That's the same as, incidentally, this is the same as T mu mu. Contract the one, contract the 2 indices. The right-hand side here is some scalar that's made out of the energy momentum tensor. It's a certain scalar that's made out of the energy momentum tensor. And the metric tensor, and it's just called T, in the same way that when you contract r mu nu with g mu nu, you get just plain old r. It's a standard notation. When you contract a tensor with g mu nu, the resulting scalar carries the same letter that the tensor started with. All right, so let's see. So what do we have then? We have minus r equals kappa times t, where T is a thing made up out of the energy momentum tensor by contracting it with with g mu nu. Now we can rewrite this. Plug in for r over here, its expression over here. Now let's see what we get. We get r mu nu minus 1/2 G mu nu times R, but R is equal to minus K. So that'll eat up the minus sign here. There'll be a K here times the scalar of energy and momentum, T. That's not the energy density, incidentally. More complicated. It has T naught naught, it has T11, it has T2, 2, and so forth. That's equal to K T mu nu. And now I can take this over to the other side and write it that the Ricci tensor is equal to K times T mu nu minus 1/2 G mu nu times T. So Einstein wasn't so far off. There is a form of the Einstein equations where it's just the Ricci tensor is equal to something, but it's not just the energy momentum tensor. It's the energy momentum tensor minus 1/2 G mu nu times T. It sort of looks kind of like the Einstein tensor, except made up out of the energy momentum tensor instead of the metric. A funny kind of duality to the equations. One form, the equations are a kind of Einstein tensor made up out of G mu nu is equal to T mu nu. In the other form, it's a kind of Einsteinish looking tensor made up out of T mu nu is equal to R mu nu. These are the two forms of Einstein's equations. And this form happens to be convenient for sometimes solving the equations. All right, let's see. Should we quit at this point, or should we go on a little more?
Class next week?
Yeah, there's a class. Well, what's next week?
They had none scheduled for next week.
Well, that's because the students are away for Thanksgiving, and but I'm here. Let's see. We don't meet on Thursday, right? We meet on Monday. We meet on Monday. Yeah. All right. The next step is to actually. Let me just tell you what the next step is. The next step is we're going to make the approximations of slow things, slow weak fields on both sides of this equation here. What we're going to find out is that the left-hand side, which is made up out of two derivatives of the metric, the most important components of it are just del squared phi, or del squared G naught naught. We're going to find out that this is good old Newton's or Laplace's del squared phi on the right-hand side. And on the right-hand side, since the only component of T mu nu which is large and significant is T naught naught, all the other components are small, what we're going to get on the right-hand side is going to be T naught naught, or the energy density. So we're going to find that in the approximation where Newton is a good approximation, the time component of this equation, 2 times, is basically del squared phi is equal to something involving the energy density, and that's going to tell us the relationship between K, or kappa, and 4 pi g. It is not quite that K is equal to 4 pi g. Why not? The reason is
Small. Small.
What's small?
Plus small.
No, it's not plus. No, that's not the reason. No, we're just trying to track down a constant now. It's this difference between phi and G naught naught, the 1/2. What we're going to find out is K is 8 pi g instead of 4 pi g. It's just this 1/2 in the relationship between the Newtonian potential and the metric. So we'll do that next time. We'll work through that. We'll do the approximation on R naught naught. We'll see that it's basically del squared phi. And on the right-hand side here, we'll find that the right-hand side is basically the energy density. And that'll help us identify the relationship between Newton's constant and kappa. But basically, kappa is Newton's constant times an 8 pi.
Question?
Yeah.
This is premature. Since there's only one class left, will the cosmological constant
Phi.
appear to there?
cosmological constant goes, depending on which side of the equation we put it, we can put it on either side of the equation. No, we haven't addressed it yet. We could do that very fast, but we won't do it. We'll do it next time. But it's another term in here. Yeah, we can do that. Remind me next time to do that. It's really a one-line thing.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.